Yes, this is a tandem presentation that deals with something which is also present in almost all previous presentations, that are the surfaces of materials interacting with biomolecules, cell, and so on, except that in the first presentation by Professor Carters. But anyway, there is something that is also common with his lecture, because our approach is to try, as an attempt, often frustrated, to transfer the molecular level of the investigation, for instance, of the molecular structure at the level of proteins and so on, try to understand what actually occurs when at the interface between a material of any kind and biomolecules. Of course, this also initially focusing on how surfaces are made. And because matter of frustration, of course, also our title was quite provocative, modeling or experiment, but at the end of the presentation, we opt to convince you that is modeling and experiments in a synergic way. Well, the important role of the surface structures when materials of any kind interact with living matters has been reviewed at the beginning of this millennium by Professor Casimo, who actually reviewed a lot of work carried out in the field of biomaterials that, when started this branch of science, was just a matter of mechanical engineering, establishing the causal sequence that is well accepted of what occurs when any materials interact with a biological medium. And then step by step, of course, there is something which is related to the hydration of the surface, and this can have a significant impact on the fate of the social proteins. And then, of course, this is the layer where the cells can interact. And almost a decades later, of course, there is this quite famous paper by the group of Dawson, what the cells see in bionanoscience, establishing the concept of the biological identity of particles. And actually, what also changed during these almost things here was that basically we moved from the domain where cells and molecules move into the materials. This was the domain of implants for orthopedy and dentistry, to the nanomedicine, where conversely are small materials that are moving towards cells and tissues. And also already Ivana reported about this. But in some case, anyway, surfaces can also interact directly with some part of the cells. And this is what was proposed, for instance, in the case of the internalization of silica particles, not only amorphous but also crystalline, where the materials are cleaned by the action of enzymes in the phagolysosomes. And then in that specific case, quite surprisingly, the surfaces are naked and can interact directly with membranes. Well, what I want to share with you are some of our findings and concepts on two of our case studies, one dealing with nanohydroxyapatites and the other again with nanosilicas, in the first case with proteins and membranes. But with this approach, looking at the atomic structure of the surfaces and trying to understand if, and if yes, how this atomic arrangement can have an impact on the structure and on the fate of what occurs on their surface. Starting from the first materials. Why to be interested in nanohydroxyapatite? Of course, because they are the synthetic materials mimicking the mineral phase present in our bones. Okay, it is intrinsically biocompatible and so on. And this is just to show what, in my mind, is quite nice. Apatites in our body, and then this is, of course, source of inspiration. In my mind, is also a matter of, well, I'm a chemist, and in synthetic chemist, in particular green chemist and so on, recently was developed the concept of atom economy, then produce molecules saving atoms. And in my mind, as a chemist, this is a case of element economy in our body, because anyway, the chemistry and the metabolism of phosphates, which of course are exploited in nucleic acids, membranes, and so on, is used, the same building block, with calcium, which is ubiquitous, to produce these highly insoluble salts that constitute, in the form of nanoparticles, the mineral phase, mineralized in the collagen of our bones. Well, in order to mimic these materials synthetically, of course, the first target is to try to reproduce size and shape. And this transmission electron microscope of the apatite particles from a natural bone, and they can appear, depending on the orientation with respect to the electron beam, as dark and long projections, but these are just platelets, nanosheets, oriented along the electron beam, and conversely, when they are perpendicular to the electron beam, they appear as a kind of flakes. Well, in collaboration with the colleagues of the Italian Institute for Ceramic Materials in Faenza, it was possible to prepare good equivalent of these natural synthetic materials in the form of platelets, less elongated, but anyway platelets of this material. And I'm a surface chemist, and from my point of view, what was highly interesting is that these particles, quite homogeneous in size and shape, each of them was highly dominated by basically one kind of surface. That with the Miller index code is indicated by these four numbers, O minus 1 bar O. That, well, in looking at the surface properties, when a scientist encounters a particle like that, a correct supposition is to suppose that the surface chemistry and physical chemists should be dominated, of course, by the most extended surfaces. And this is the case. But there is something peculiar in that surface of hydroxyapatite, because from a crystallographic point of view, the surface is that one. But from a chemical point of view, you can have three different scenarios. And this also results from modeling, okay? And then depending on which is the actual chemical termination of the surface, one can have on different particles, or even on the same surface of one particle, of the same type, this kind of termination, so-called stoichiometric, that one called calcium-rich, or another one called phosphor-rich, where actually calcium-rich, epi-rich simply means that the topmost layer is constituted by a different arrangement, a relative amount of calcium cations, here in gray, and in phosphate ions. But from a crystallographic point of view, it's exactly the same surface. Fine details in the difference of the structure, but actually this is the structure that is exposed towards molecules. And then, of course, the question is, are these different atomic arrangements at the same kind of surfaces relevant for the interaction with biomolecules, for instance? Then, of course, that the first step in order to be able to answer this question is to have a method to reveal the presence of these different termination, and possibly not the absolute, this is a dream, but at least the relative amount. And this was the results of a first synergy between experiment and modeling, and I will skip off technicalities. Maybe that most of you can imagine that in order to distinguish these different kind of surfaces, what not to apply some special microscopy. And maybe that some, if not most of you, have some familiarity with scanning microscopy of this kind, a tip scanning a surface. But of course, we are looking at atomic resolution. At 4 nanoparticle, forget it, for most cases, including this one. And then, in principle, here we have something vibrating on the surface, and then there is a light that is monitoring what occurs to the oscillators. And then, from a chemical point of view, we can substitute this physical tip with the finest tip of surfaces, which are molecules. And for instance, to substitute this physical tip with a chemical one, these are carbon monoxide molecules, which are adsorbed on the sides. They oscillate, they vibrate, and by infrared spectroscopy, we can monitor this vibration and understand which is the nature. Of course, this is a matter of chemical resolution and not longer spatial resolution. But anyway, this is the method. Well, modeling demonstrated that the carbon monoxide adsorbed on calcium-rich per-Richard stoichiometric surfaces of that surface of deoxyapatite can produce different signals. And just by quite complex matter of data analysis, it was possible to establish that among all possible combination of the spectra produced by different type of surfaces possibly exposed, in experimental real cases, the experimental signals can be fitted just by a real low number of experimental of theoretical possibility. And this allows us to establish which was the actually relative amount of the different atomic arrangement exposed at the same kind of surface. Well, taking the story short, then again in collaboration with our colleagues in Scienze, it was possible to prepare many different kinds of these nanohydroxyapatites, and among them, in particular, 2 were highly equivalent in terms of morphology and other surface properties, but significantly different in the ratio between the 2 different types of termination of the same crystallographic surface. The ratio was reversed. 1 to 2 and 2 to 1. And then we challenge our systems trying to absorb a protein, related to the question that Gianfranco posed to Ivana. Of course that you can have on one end a pool of actual proteins, on the other some kind of model or test protein. And this was our case, and then BSA, okay, because it's well known, it is cheap and this is important and so on. Well, and in this case, what we found is that even these fine differences in the detail of the atomic structure of these materials have actually a relevant impact on the fate of the absorption proteins, both in terms of amount, for instance, in this case, with a larger fraction of these different atomic arrangements, so-called calcium-rich. For instance, we obtain multi-layers of adsorbed proteins. In this case, it was possible to investigate the structure of adsorbed proteins by CDUV, and actually, in this case, even if in multi-layer, the structure, the average structure of the multi-layers was better preserved with respect to the native form. Conversely, here the absorption was more limited, but the secondary structure was actually highly transformed. And coming back to the story, what actually then is exposed towards the exterior of this mixed hybrid surfaces, materials, and protein, then we measure an average property of the materials, that is the zeta potential, and as you can see, these are the naked materials, and this is after absorption of the protein, and we obtain an opposite evolution, indicating that what actually exposed towards the exterior by the proteins was different, was the same protein, but the structure of the protein exposed toward the exterior was completely different in the two cases. Why? Actually, because it should have been different, the interaction with the surface. This can be interesting from an experimental point of view, but still a fundamental question remains. Well, you know very well this tail, now it's kind of nanotail. For instance, we found that in some case we have a multi-layer of proteins, and in another case not. But what actually the origin of the different phases is something which is occurring there, at the interface. And at the molecular level, it is actually extremely difficult from an experimental point of view, have a look precisely there. And then, as I hope that Professor Ugliengo will show us, modeling might help in this respect. And just a few words about the other case study, nanosilicate membranes. Ivan already reported about silicas and proteins, but in this case, the focus was on what actually can occur when the silica surface can interact directly with membrane, for instance, in this case. And the starting idea to investigate in subdepth this aspect stems from the new finding at the Scansetti Center, thanks to the research work by colleagues Francesco Turci, Cristina Pavà, Mauro Tomatis, and Vice Fubini, who in the last year focused on the surface signals as key descriptors of silica hazard, in particular of crystalline silica, quartz. But independently on crystallinity or the amorphous state, this just to recall or introduce to some of you which are not familiar with the surface silanols. Basically, from a chemical point of view, we can imagine two functional groups, then silanols and siloxane bridges. From a chemical point of view, the silanols are the more active and interesting one. And there can be different arrangement of silanols that can be studied and investigated by different means, but vibrational spectroscopy, in particular in the infrared mode, can provide information, in particular studying this vibration, among all the others, because this is highly sensitive also to the distance between silanols. You have a reference signals, and then these signals shift, and is modified, is broadened as a function of the strength of the interaction that is a function of the distance between the silanols. And what is highly interesting in our opinion is that we have the chance to find the condition in order to selectively remove from the surface of nanosilica families of silanols differing from the density. And for instance, through a first thermal treatment, we were able to remove selectively all silanols close enough to interact to hydrogen bonding that represented almost 30% of the surface. Then remove selectively another kind of silanols that, thanks to the calculation of Piero Ugliengo, were found to be silanols at a specific distance, around 5.5 Armstrong, basically leaving only highly isolated silanols. And what was surprising and interesting for us is that when evaluating the membranolytic potential of this material, substituting as a model the membrane of lysosome to the membrane of red blood cells, the selective removal of these specific pairs of selenors. And from a quantitative point of view, here we have just changes of 15%, the amount of selenors present on the surface. Oops. No. Well, this has a huge impact in terms of decrease of the permeability potential, indicating that likely there should be some specific arrangement of this otherwise common surface size that could play a relevant role in destabilizing membranes. And of course, this is matter for future investigation, and we hope that among them we will be able to include also modeling. Thank you.
You immediately see from the title that we are focusing on modeling now. And then the question is, if we would like to study human body, we are facing a variety of different materials from hard to soft. And our question, our key point is, can we, from structural detail, design new biomaterials which can replace pieces? And of course, the answer is yes. And there are a huge variety of biomaterials which can be used to integrate with living tissues. But the question is how they will talk to the living organism. And the key is the surface, as we have heard this morning many times. And clearly this is a very delicate business, because you may think that, for instance, a titanium implant is just talking directly to the body fluid, but this is not the case, because we know that a nano layer of titanium oxide is really the surface in direct contact with the body fluid. So if we really would like to understand this kind of integration, we really have to know the surface details. But here the problem is very complicated compared to what we are doing daily on catalysis business. This is a surface science model for biology that we are faced to, and this is far less developed than the catalytic model, due to the incredible complexity, as we have seen before, of the contact between, let's say, an inorganic material and a living organism. For instance, talking again about fibrinogen, which is known from the structural details, from X-ray diffraction, from high degrees of precision, of accuracy. We know basically where the atoms are. But as soon as you put this molecule on the surface, atoms are blurred, and so you only see basically domains. And the atomistic view is completely lost. And as we have just heard, the atomistic view is essential if we would like to make progress in this direction. And so the question is, can modeling help in that respect? But what is modeling? Modeling has been defined by these bright guys in the 50s as a mathematical description. A simulation is a mathematical description or a model of a real system in a form of a software, a piece of software, of a computer program. And within this computer program, we have to code the equations dealing with that particular system we would like to simulate. And unfortunately, for atoms and molecules, the equation, the master equation, is the Schrödinger equation. And the Schrödinger equation is certainly beautiful, but basically unbreakable. You cannot solve this equation but for very, very small systems like hydrogen atoms and few others, which are far away from the complexity we are dealing with. And fortunately, in the 60s, there has been a huge step forward, the solution of Schrödinger equation, in which instead of this focusing on this beast, the wave function, which nobody knows the real meaning, Kohn and Sham were just supporting the idea that is enough to focus on electron density. the observable from any X-ray diffraction experiment. And if you are able to find out a special functional acting on this electron density, you get the energy of the system, which is exactly what the Schrödinger equation is giving you, but at a very, very high price compared to DFT. And so DFT has opened a completely new world to simulation. We can really attack significant systems. Now, for instance, if you would like to simulate hydroxyapatite, which is, as we have heard from previous talk, is the main constituent of bones and teeth, well, I mean, a quantum mechanical approach can give you the following, can give you the electrostatic potential felt by molecules at the surface. And so from that, you can figure out a specific interaction between molecules and surfaces. And for instance, you can try to answer the following. Will protein interact directly or through water layer with an exposed hydroxyapatite surface? Seems a simple question, but it is very complicated. Basically, nobody knows exactly this to answer this question. And of course, I mean, if you think for a while, this is a completely, extremely huge and complicated system to model in a computer, because you have the body fluid, you have water, ions, the protein. You have to be correct as far as the conformation of protein is concerned, and so and so. So the nice thing about modeling is that you have to figure out a sort of reductionist process in which you reduce the complexity of this question to another one. For instance, just removing the complexity of protein and just focusing on its constituent, amino acid, for instance, glycine. And the question now is much more easier to understand. For instance, are we able, through computer simulation, to see if glycine is interacted directly or through water layer? This has been certainly addressed by us, but by many others as well. And so we simply simulate a piece of hydroxyapatite, and then we compare the energy. And as you can see, all the atoms are there. We need an atomistic view. We compare the energy of absorption of this glycine through mediated, decorated by, with the surface decorated by water, with respect to the one in which glycine is interacting directly. And as you can see, the answer is clear. Glycine prefer to make direct contact with the hydroxyapatite surface. This does not at all solve the previous question. There is a life of work to be done to move from this simple toy model to the real system. But, I mean, this is the way to go. Now, let's switch to a different, completely different material. So silica-based, we have heard a lot this morning. And there is a nice material which is basically a periodic replica of voids in which the walls are silica, amorphous silica. And I mean, the nice thing about this material is that these mesopores can host molecules, drugs, for instance, or even proteins, small proteins. And then clearly this is ideal for doing drug delivery system in which you are just storing drugs in these caves and then deliver the material at the target organ. And so you are protecting the drug from metabolic processes up to the point in which it's really useful. And then the question we would like to ask is, what are the driving force for drug absorption? What is the energetic of interaction? How strong is the energy of interaction? What is the state of the drug inside the carrier? Beware that this kind of questions are now on the wishing list of FDA, because they would like to know exactly the interaction between a drug and an excipient or a carrier. So modeling can provide such a thing. Of course, this is a pretty complicated system, but it's doable. And we have been able in the recent past to design an explicit atomistic model in a computer mimicking the MCM 41 and trying to see if we can understand what's going on when we absorb ibuprofen, which is a quite common drug. And then we do everything ab initio, in other words, using the DFT that I just showed before. So these are pretty heavy calculations, so we need high-performance computing facility, which are available in Europe through projects. And then, for instance, we are able to give fine details about atomistic interaction, and we can also study the high loading, different loading of the drug in the silica. And we can also have, as a byproduct, the energy of interaction of this molecule. And surprise, surprise, you will see that, this red bar compared to the blue one, in the red bar, dispersion is included, London forces, and in a blue one are not accounted for. And as you can see immediately, dispersion is absolutely essential if you would like to really accurately model interaction between molecules and materials. And we can do more. For instance, this is what you get from the infrared spectrum of ibuprofen in the mesoporous material, and this is the result of the simulation. And so you can really interpret fine details of the infrared bands, which are basically very difficult to explain without an atomistic model. The same is true for NMR prediction. As you can see, this is from the experiment, and this is our prediction. And so really, modeling can provide essential features about structure and energetic. And one question which is always present in such a kind of topics is the drug isolated while interacting with the surface, or is making dimers? In this case, this is a carboxylic acid. And so the carboxylic acid tends to stay as a dimer. And this is quite important for the drug delivery, for the kinetic of delivery. And so again, we can do a very clear distinction between the two through energetic, and we will discover that the surface is able to break the dimer due to the interaction with the silanol groups at the surface. So in conclusion, basically the experiment relies upon different instruments, different pieces of hardware and software. So you may be doing NMR, calorimetric, X-ray diffraction, and each piece is made of a specific knowledge and skill. But modeling is something more universal, because you have an equation which is capable in principle to deal with all these aspects, from structure to energetic to spectroscopy. And so we feel that thanks to the computer technology that is still growing very fast, modeling will be an essential tool to be combined with any experimental investigation. Thank you very much for the attention.